Welcome. This is a Z Academy, a place where you can learn about topics in machine learning, deep learning, and artificial intelligence. Latent Spaces Part 2, a simple guide to variational autoencoders. In the previous tutorial, we learned about latent spaces, autoencoders, and their implementation in TensorFlow. In this tutorial, we shall extend the concept of autoencoders and look at one of the special cases of autoencoders called variational autoencoders. More specifically, you will learn what is a variational autoencoder, how to implement it using an autoencoder architecture, how to use it to generate new images, how to explore the latent space using a latent distribution. Variational autoencoders. The main strength of autoencoders reside in their ability to extract the abstract representation of the data space, which is supposed to handle unseen instances. This opens possibilities where one could generate new images that have not already been seen using the latent space. The general autoencoder architecture, however, does not allow much freedom in traversing the latent space. This can be circumvented by VAE autoencoders, which learn a latent distribution instead of a single latent vector. Therefore, it becomes viable to interpolate in the latent space. More specifically, a VAE autoencoder models a multivariate Gaussian distribution which assumes that data can be approximated as a normal distribution. An example of such architecture is shown in this figure. The VAE autoencoder enforces a prior on the latent vector a multivariate Gaussian distribution, which maps the input onto the latent space in contrast to a single multidimensional point in latent space as in general autoencoders. Let's look at the loss function computation formulation for a VAE network. Just like autoencoders, VAE also learns by optimizing an objective function, which is a loss function computed for every data instance. However, the loss function for VAE is different from autoencoders in that they not only minimize the reconstruction error but also enforce the constraint that the latent vector comes from a normal distribution. This is achieved by adding an additional term in the loss function as shown in this equation. The reconstruction error is computed as usual between the input image and the output of the decoder and can be modeled as a mean square error as it is shown here. The divergence error can be computed using Kullback-Leibler divergence, which is a measure of how one probability distribution differs from another one. Since the assumption is that the data comes from a normal distribution, so we can compute the divergence loss as it is shown here. Implementation. Similar to our previous tutorial on autoencoders, we will use an open-source data set from Cogla Datasets. You can download it from the link in the description. This tutorial will require TensorFlow 2 and Jupyter Notebook installed, so if you haven't had it set up, you can either use Google Colab or set it up on your computer using Anaconda. Now let's build the model. Just like autoencoder, VAE consists of three sections: an encoder, a latent vector, and a decoder. However, since latent vector in VAE comes from a normal distribution, there is an additional layer which maps the encoder output to the mean and variance of the probability distribution. The latent vector is then sampled from that learned latent distribution. We build the model of VAE similar to autoencoder. First, we import the necessary Keras libraries. We define the layers of the encoder. Then we introduce a sampling function to construct the latent vector, and then we decode the sampled latent vector by projecting it onto the latent space. We start with an input layer of image size 128 by 128 by 3. Then we add 3 convolution layers, each followed by a batch normalization. The batch normalization helps to keep the output within normal distribution. We then add a dense layer followed by 2 distribution layers, that is the mean and the variance of the distribution. The encoder looks something like this. Pause the video for a while and see if you understand the output and how it relates to the code. The latent vector is then sampled from the mean and variance layers. A sampling function which takes the output of the mean and sigma layers of the network is shown here. We define it as a Python's lambda function, which means it can be attached to a layer in the network and its value is computed on the fly during the training. The decoder takes latent distribution as an input and generates a 2D image. We start by adding a dense layer, which is reshaped into a 2D array in the following layer. The dense layer is followed by a set of inverse convolution layers. Each inverse convolution layer upsamples the image and is followed by a batch normalization layer. The number of kernels learned at each layer are gradually decreased in the successive layers. The convolution layers are continued until the original image size is reached. A prediction is obtained by passing the lambda sampling function to the input layer of the decoder network. The layers of the decoder look something like this. Go ahead and pause the video. See if you can understand it and how it relates to the code. Now let's train the model. The training is performed using the loss function as we defined in the previous section. The total VAE loss, including both the reconstruction and the divergence loss, is computed and added to the training model as here in this code sample. The custom VAE loss function is added to the model using its addLoss function. Then the model is compiled using the Atom optimizer and run for a number of epochs. Let's look at the results now. These are some of the images randomly sampled from the latent space. More specifically, if we generate a random mean and variance vector and then pass it to the decoder of the network, then it generates images as shown here in this figure. The main advantage of using a VAE instead of autoencoders is to have the ability to generate new images which are not already present in the data set. We explore this in these results. Using the VAE model that we trained in the previous section, we generate new images by sampling from the learned distribution. We first take a sample source image and a target image from the data set and project both into the latent space by using the encoder. We then take the mean of the source and the target latent vectors. All three latent vectors, the source, the mean, and the target, are reconstructed using the decoder. This median image is the new image that inherits the characteristics of both the source and the target image. A set of such mean images along with their respective source and target images are shown here in this figure. We can then extend this concept further and generate several images in between two images instead of just one image. Since we know that both latent vectors come from the same distribution, we can interpolate between the two latent vectors and thus generate as many intermediate steps as we desire. The result of such interpolation can be viewed here in this figure. Since the data set consists of multiple diverse products, it is impossible to learn a global distribution that covers all the instances. However, we expect that VAE at least might have learned multiple distributions, thus covering the various categories in the data set. In order to observe this, we take some images from the data set belonging to a certain item, for example, shirts, shoes, etc. Then we take some random images from the sample which we split into source and target images. Then we generate interpolated images between the randomly sampled source and target images. In this tutorial, you have learned how to construct a VAE autoencoder and how to use it for the generation of new images. There are many potential applications of VAE, whether it is the generation of new redundant objects in virtual environments, for example, trees, building facades, etc., or predicting an image estimate, for example, age-based image deformations. VAE can be very useful. Keen observers might have noticed the rather blurry reconstructions of the VAE. This is due to the fact that it uses KL divergence loss, which hinders in convergence of reconstruction loss. One way to mitigate this is to reduce the weight associated with KL divergence. However, doing this can make VAE act more like standard autoencoders. We will learn about another generative architecture called GAN, Generative Adversarial Network, in the next tutorial, which doesn't suffer from this problem. You can practice the code using Python Notebook. The link to the code is in the video description below. Thanks for watching the video. I hope that you have learned the concepts in this video, and it would improve your understanding and knowledge. Feel free to post your question in the comment section below. If you find this content useful, please like, share, and subscribe to the channel.